Today, we are diving into a really fundamental shift in how blockchains work. We're talking about how they're evolving from these slow, kind of single-track systems into something way faster, way more powerful, basically how they're getting a second brain.
So here's our game plan. We're going to start with a big problem that's been holding blockchains back. Then, we'll introduce this idea of a second brain. After that, we'll get into the cryptographic magic that makes it all possible, show you exactly how it works, and finally, we'll look at the absolutely incredible future this is about to unlock. All right, let's jump right in with Section 1, the blockchain's big problem, which all comes down to something called the synchronous bottleneck.
I mean, it's the question we've all asked, right? With all this amazing innovation, why does using a blockchain sometimes feel like you're back on a 56K modem? So slow, so expensive. What is going on?
Well, the answer is actually pretty simple, but it has huge consequences. In a traditional blockchain, every single computer in the network has to do the exact same work. It doesn't matter if it's a simple little transfer or a super complex calculation. Thousands of computers have to run it and all agree. Now, this makes it incredibly secure, for sure, but man, is it inefficient. So, how in the world do we get out of this jam? Well, the answer is a totally new approach, an asynchronous one. It's about giving the blockchain that second brain we talked about. Just think about it. What if, instead of forcing the main blockchain to do every single little thing, we could just give it an assistant? A powerful coprocessor that sits on the side, handles all the really intensive work, and then just reports back with the final answer. That is the whole idea behind this new asynchronous architecture. And you know, this isn't just a fun metaphor. It's a real concept called outsourcing verifiable computation. Now, the two most important words there are verifiable and proof. We're not just going to trust this second brain to get it right. No way. We're going to demand that it proves, mathematically, that it did the work correctly. And this is just so crucial. Because, as this quote from HackMD points out, the old way of outsourcing work meant you had to use blind trust. You just hoped that the company you hired wasn't being lazy or malicious or just made a mistake. And that trust issue is exactly why this idea was a non-starter for so long. Until now.
So what changed? What was the breakthrough? Well, it's a piece of cryptographic wizardry called a ZK proof, and this is what makes the whole thing possible.
A zero-knowledge proof, or a ZKP, is, well, it's a genuine game changer. It's a way for our second brain, the prover, to convince the main blockchain, the verifier, that it did a computation correctly without showing any of the private data or the steps it took. It's like saying, I know the secret password, and here's a magic trick that proves I know it, but you never ever have to say the password out loud. ZK proofs basically give us trust without needing to trust a person or a company. They rely on three mathematical guarantees. Completeness means a true statement will always get a thumbs up. Soundness means you can't fake a proof for a false statement. And zero knowledge means all your private data stays private. It's this perfect cryptographic trifecta that gives us total mathematical integrity.
The way it works is this really clever back and forth, almost like a dance between the prover and the verifier. The prover makes a commitment, the verifier sends back a random challenge, and based on the response, the verifier knows, with mathematical certainty, that the prover did the work correctly, all without seeing any of the sensitive info.
Okay, so that's the theory, and it sounds kind of like magic, right? But how does this stuff actually work in practice? Let's look at how it started with just batching simple transactions and grew into something that can handle basically any computation you can think of. So the first big use case for this tech was something called ZK rollups. The idea was pretty simple. Take hundreds, even thousands of transactions, handle them off-chain, where it's cheap, and then roll them up into one single tiny proof that gets posted to the main chain. This was a huge step forward for cutting down on fees and network congestion. But the real revolution, the thing we're talking about today, is the general-purpose ZK-Coprocessor. You can think of it like a ZK virtual machine or ZK VM. This isn't just about batching simple transfers anymore. No, this is a full-blown engine that can run any program you throw at it and prove it was executed correctly. So something like calculating a user's 30-day average trading volume, that's way too expensive for the main chain. But the coprocessor can do it off-chain in a flash and just send back the proven result. This is the true second brain. Okay, to really see how this works, we just need to get three key terms down. The guest is the actual program, the piece of code we want to run. The host is the powerful off-chain computer that actually does all the heavy lifting. And the prover is the special part of that system that generates our magic ZK proof.
And this image shows the whole process beautifully. Our guest program runs on the host system. As it's running, the prover is watching, and it generates what we call a receipt. And this receipt is the ZK proof we've been talking about. It's just a tiny, cryptographically secure file that proves, beyond any doubt, that the program ran exactly the way it was supposed to. And this is the most important part. Instead of bogging down the blockchain with a massive, complex computation, you just send it this tiny little receipt. The blockchain can check it in milliseconds, instantly confirming the result without ever having to rerun the whole thing itself. It is an unbelievable leap in efficiency. So that brings us to our last section, the asynchronous future. Now that we have this incredibly powerful new architecture, what does it actually let us do? What does it unlock?
Well, first, let's just talk about money. ZK-Coprocessors absolutely obliterate costs. I mean, look at this. ZK-Sync, one of the big projects here, has shown transfer costs of about 1/100th of a penny. This isn't just a little bit better, it's a completely different world.
And when computation becomes essentially free and verifiable, a whole universe of new things becomes possible. Suddenly, stuff that was just a pipe dream is now totally feasible. We're talking real-time financial settlement, we're talking about actually verifying the output of an AI model on-chain, even building apps that can work across different blockchains without a hitch. The list just goes on.
You know, the only real bottleneck left is how fast we can generate these proofs. And that has kicked off a massive race to build specialized hardware. GPUs are what we use today, and they're pretty good. But now companies are building custom chips, first FPGAs, and eventually ASICs, that do nothing but generate ZK proofs at absolutely insane speeds. This is what will make these systems feel totally instant.
And this quote from the team at ZK Sync really just says it all. Ultra-fast ZK isn't just about making things cheaper. It is a breakthrough technology that opens the door for entirely new kinds of applications that just weren't possible before.
And so that leaves us with this one final, really exciting question. This shift from synchronous to asynchronous computing, powered by these ZK coprocessors, it might just be as important as the invention of the blockchain itself. So if any computation, no matter how complex, can be proven on-chain for almost nothing, what kind of problems can we solve next? What does a world built on cheap, verifiable truth actually look like? We're really just starting to find out.